Ladies and gentlemen, tonight's lecture, and that's all you'll have for homework tonight, is just notes, is on gases, liquids, and solids, and then we're going to start talking about intermolecular forces. This is chapter 11 that we are starting on, chapter 11, and we're going to be covering sections 11.1 and 11.2. So my recommendation is to read those after you watch this lecture, to pick up any of the little examples that need to be picked up. So let's first start talking about what intermolecular forces. And intermolecular forces are going to be forces of attraction or repulsion, and we talk a lot about attraction mostly, that happen between neighboring particles, and these could be atoms, molecules, or ions. And these forces are weak compared to the intermolecular forces, or excuse me, the intramolecular forces that hold a molecule together. So to give you an example of what we're talking about here is we can use water as an example. And so we know that water has covalent bonds, single covalent bonds. And so if we were talking about the intramolecular forces, these intramolecular forces, we'd be talking about the bond, that covalent bond, that sharing of electrons between the hydrogen and the oxygen. That would be the intramolecular forces. Those are pretty strong. It takes a lot to break that bond between the hydrogen and oxygen. Now, as far as the intermolecular forces that we're talking about the force of attraction from one water molecule, and we'll represent that by 3 dots. And let's not confuse those dots with bonds, and let's not confuse those dots with electrons. They're none of those. They're just, these guys are representing, well, maybe we should do them in red. They're representing a force of attraction between those molecules. And let's say another water molecule over here. And that's this force of attraction between these two water molecules. Now, why are they attracted to each other? Well, mostly because water's polar, and on the oxygen end, because it is more, oxygen is more electronegative, it will pull those electrons closer. You're going to get a slight negative charge, and on the hydrogen end, you're going to get a slight positive charge on both of those. And so because you have these slight negative and positive charges, you have these forces of, so that should be a negative there, scratch that out, delta positive, delta positive. You have this force of attraction. These two water molecules are slightly attracted to each other, and so that's what we're talking about when we talk about intermolecular forces. Now, something that's really important to keep in mind too is the state of matter of a substance depends largely on the balance between kinetic energies of the particles and the intermolecular forces. So let's kind of address that down here a little bit. And this is some stuff that we've seen before. One thing is we can have a transfer from something that's a gas, or a phase change, we should say better, a gas to a liquid and to a solid. And we can do this a couple different ways. So let's say we have a gas here, and in a gas we've got these gas particles, you know, they're bouncing off the walls of their container, they're bouncing off of each other and things like that, and they're moving really, really rapidly. Now we can slow them down by cooling them. We can also compress them into a smaller volume, and we can do that through high pressure, and that's going to cause them to turn into a liquid. And liquid molecules are going to have a little bit more of a rigid, we won't say rigid, but a little bit more orderly shape. The particles are still moving, but they're kind of not moving as rapidly and as fast, and they don't have the freedom of motion. They're not as far apart as they are in gases. Now, if we continue to cool these guys, we know, and this is the case of water, they're going to solidify into a solid. You got very organized arrangements, very close together. Now we can flip this all around and make it go the other way by just adding heat. We know if we take some ice, which is just nothing more than solid water, we can turn it back into water by heating it up, and those molecules start moving faster, and they break those intermolecular forces that are holding them together. And then we can continue heating or even reducing pressure, and we can turn things back into a gas going in this direction. So you know, that's the kinetic energies of those molecules, but we can also deal with some intermolecular forces that's going on. Once again, those intermolecular forces are the force from one molecule to a different molecule, those forces of attractions that we see here. Now, just to give you kind of an example of what we're talking about here, we can talk about our halogen diatomic molecules. Now, if you remember, our halogens are our group 7A's. And those diatomic molecules in the halogen are fluorine, our chlorine, our bromine, and our iodine molecules. Now, the states of matter at standard state, which would be 25 degrees Celsius and 25 degrees Celsius and 1 atmosphere, are interesting because these guys are all in the same group. They all have the same number of valence electrons. But fluorine is going to be a gas at 25 degrees Celsius and 1 atmosphere. Chlorine is also going to be a gas. But bromine is going to be a liquid. And iodine is going to be a solid. And so our goal for one of the goals for tonight is we're going to be able to explain why is it that fluorine and chlorine are gases and bromine's a liquid and iodine's a solid. What's the reasoning behind this? And it does have to do with what we call intermolecular forces, IMFs, intermolecular forces, IMFs. Intermolecular forces explain this. They explain why it is that one fluorine molecule is not necessarily very attracted to another fluorine molecule, but one iodine molecule kind of is a little bit more. So let's kind of scroll down here and start talking about, and we'll jump into 11.2 now, the types of intermolecular forces that we have. Now, one thing that I think we do need to keep in mind is that these intermolecular forces do tend to be weaker than an ionic bond or a covalent bond. And so consider the molecule HCl. Now, we know an HCl is going to look like this. If we draw the Lewis dot structure of it. And we also should be able to recognize this guy as a polar molecule. Chlorine is much more electronegative than hydrogen, so we're going to have definitely a dipole on this molecule. Now, if we want to vaporize HCl, and meaning vaporize, we're just going to take HCl in its liquid form and turn it into HCl in its gaseous form. We're not breaking the bond that holds the hydrogen to the chlorine at all. When we vaporize this, we don't do that. What we are doing is we are breaking, or overcoming, we should say, the intermolecular force between one HCl and another HCl. And there's that intermolecular force due to slight negative charge on the chlorine and a slight positive charge on the hydrogen. So when we vaporize it, we just basically overcome that intermolecular force. And it's very low, 16 kilojoules per mole, so it really doesn't take very much heat to vaporize. Whereas if we were to look at the bond, the covalent bond between the hydrogen and the chlorine, and we want to break this bond here, this is the bond we're trying to break, it's going to take a lot more energy, 431 kilojoules per mole to break that bond. So the whole point is, intermolecular forces are a lot weaker than a bond, whether it be ionic or covalent. Okay, a couple of things that we can look at when it comes to intermolecular forces, and one of those is boiling points. And this is just going to be the temperature at which something turns from a liquid to a gas. These reflect the strength of the intermolecular force. Melting points also can be reflected in the strength of the intermolecular force, or the IMF. And typically we say that if you have a greater boiling point, I'm going to abbreviate it BP, it means you have stronger intermolecular forces occurring in those molecules. Okay, and we're going to come back to this, and we'll kind of look at this with a table with some types of substances. But let's get into, first off, basically our 4 types of IMFs. These are our intermolecular forces. And we'll talk about the first one here, and this is called an Ion Dipole Force. Now, what an ion dipole force is a force that exists between an ion, as the name tells us, and a polar molecule, which we say has a dipole. Polar molecules have a dipole moment. That's what's going on there. And so we can have a couple different types of interactions here. And it looks like I'm not sure what's going on with my picture here, but it looks like it got a little wonky, but that's okay. We can have what we call cation dipole attractions, and so here's our cation here in the middle. It's a positively charged particle, and that could be somebody like, hey, sodium. And then we have a polar molecule up here, and there's going to be this weak force of attraction. They're using dashed lines instead of my red dotted lines, just like that. It's not a bond, it's just a force of attraction. The opposite opposite charges attract. So the negative end of a polar molecule is going to be attracted to the positive cation. And over here we have obviously anion dipole. You have an anion, like maybe the chloride ion, being attracted to the positive charge on a molecule. And that could be water or somebody like that. And I think we're going to give that example down here below. And so here's the example, water molecule with the sodium ion. So again, if we have that water molecule, remember that the oxygen is more electronegative. It's going to attract those electrons to it. It's going to be slightly negative, delta negative. So there's going to be this force of attraction between the oxygen part of the water and the positively charged sodium, because hey, I just did that. Hold on a second. There we go. 1 plus charge. And obviously, if there was some chlorines around, they would be attracted to the negatively or the positively charged hydrogen. Okay, so that's the first type of intermolecular force that we deal with. Okay, the next type of force, intermolecular force, that we often come across is what's called a dipole force. Now, this is the attraction due to two molecules basically being polar. Okay, so in the example I gave before of like the HCl, these guys are going to, one HCl molecule will be slightly attracted to another HCl molecule because there's polarity occurring here. The chlorine is slightly negative, and then the hydrogen is slightly positive, and the hydrogen is slightly positive, and the chlorine is slightly negative. And so you have this force of attraction between these. Generally, these are going to be weaker, these dipole dipoles, than an ion dipole. So one of the things that we have to be able to determine is, do we have a polar molecule? That's one. And do we have an ion, or do we have just a couple polar molecules being attracted to each other? Something important to mention here is that for molecules with about equal mass, about equal size, the strength of the intermolecular attractions increase with increasing polarity. So the more polar you are, obviously, the more attractive you are to other molecules that are more polar, and so on. So there's a little data table here that it's an interesting data table. I'm just going to kind of focus on the first substance in the data table, which is propane, and the last substance, which is acetonitrile. So in the propane, looking at these molecular weights, they don't deviate very much, 44 to 4650. So basically 44 to 41. They're pretty close in molecular weights. But the big difference between these guys are their dipole moments measured in dBis. So propane has a very, very low dipole moment. And the reason why propane has such a low dipole moment, if we were to draw this propane molecule here, we would have 3 carbons, all single bonded, and then we would have around each carbon hydrogens. Just like that. And if we look at that, hopefully you as a student can see this is a pretty non-polar molecule. It's pretty symmetrical. There's not a whole lot going on here. And so that's what's reflected in this value over here. Whereas if we drew acetylnitrile, we've got carbon with 3 hydrogens bonded to it, single bonded to another carbon in the center, which is then triple bonded to a nitrogen with an unshared pair of electrons on it, just like that. Double check, make sure everybody's got, yep, there we go. You can see that, or hopefully you can see that this is definitely a polar molecule. This nitrogen that's on the far end, it's much more electronegative. It's going to pull those electrons towards it in this way, and so we're probably going to have a negative charge over here, slightly polar. So acetonitrile is definitely going to be attracted to other acetylnitrile molecules through what we call a dipole-dipole. And maybe there's another acetylnitrile over here. And there's that force of attraction. Now, what does this do? Well, it has an effect on the boiling point. It's easier, it takes less kinetic energy or temperature. You don't have to heat acetylnitrile or propane up as much to get it to boil, to get it to go from a liquid to a gas, 231 Kelvin. Where acetonitrile, you've got to heat it up a lot more because there is this force of attraction going on right here. So it takes more energy to break those molecules apart from each other. And I want to be real clear about that. We're not breaking apart the acetonitrile molecule. We're not breaking any bonds here. We're not breaking any bonds here. We're not breaking any of the hydrogen bonds. What we are doing is we are overcoming this force of attraction here, this intermolecular force, to get acetonitrile to boil, to go from a liquid to a gas. So really, that's what we're talking about when we talk about intermolecular forces and boiling point. Okay. London dispersion forces are another type of intermolecular force, and we call them for short LDFs. They're a type of IMF. And okay, so as we're saying, London dispersion forces, and these are what these guys are. These guys are temporary dipoles. So it's temporary on a nonpolar molecule, and it's due to the movement of electrons. And something important to keep in mind is LDFs exist in all molecules and atoms. So everybody gets these guys, and some have more LDFs or London dispersion forces, and some have less LDFs. They also sometimes just call these guys dispersion forces. So here's what it is. And so let's take a look down here. We've got this little illustration of a helium atom here. And the helium atom has 2 electrons right there, and they're kind of zipping around, most likely in their 1s orbital. Let's say it's not excited or anything like that. Now, occasionally, if you look over here, you might have both of these electrons kind of oriented on the same side of the orbital, or of the electron cloud. And if that's the case, you could have a momentarily negative charge due to those electrons being there. Now, if that's the case, you might have a slight dipole on one end of the molecule and a slight positive dipole on the other end of the molecule. And so now you could have this force of attraction, which is shown right there, just because you've got electrons over here, and some electrons over here and over here. Now, this does occur with everybody. So the ease at which this electron distribution in a molecule is distorted is called polarizability. Just a word that gets thrown out there. It's basically, sometimes chemists like to call it squishiness. How much can you distort an electron cloud? Dispersion forces tend to increase in strength with increasing molecular weight. When you have more electrons, there's a greater chance that they'll all be at one side of the molecule. Okay, so let's take a look real quick here at some boiling points of our halogens first, and see if we can relate that to intermolecular forces, and specifically relate this to London dispersion forces, or LDF. So over here on the left part of this table, we have our halogens, and we have fluorine, chlorine, bromine, and iodine. And then we have our boiling points of each one of these. And notice how the boiling points, as you go down the periodic table from fluorine, chlorine to bromine to iodine, our boiling point is increasing rapidly. The reasoning behind this is fluorine has a lot less electrons, with only 9 electrons, and so it's less likely to produce a stronger London dispersion force, where an iodine, pretty big atom, with 53 electrons in a neutral atom, and that's just one of them, and you got 2 of them going on, so you're going to double that, 106 electrons going on there. So as we increase our molecular weight, and as we increase the number of electrons, we increase the boiling point. And this is the explanation for why fluorine is at a room temperature a gas, and chlorine at room temperature is a gas, and bromine is a liquid, because there's more electrons and there's increased mass, and you're going to have more intermolecular forces, more London dispersion forces. And why at room temperature iodine's a solid. It's as simple as just London dispersion forces, what's going on there. And we have to think about this as well. If we look back to fluorine, thinking about fluorine, fluorine is a nonpolar molecule. So it can't have an ion dipole. It can't have a dipole because it's nonpolar. So the only thing it can have is London dispersion forces. Looking at the noble gases and boiling points, remember these guys are listed in the way they appear on the periodic table, going from top with helium all the way down to xenon. And we have an increasing boiling point once again, starting at 4.6 Kelvin, going up to 166 Kelvin, just due to the London dispersion forces that are occurring. And these aren't molecules, these are individual atoms, but those individual atoms of that xenon, 54 electrons, have more of a chance to cause a slight dipole, which is going to cause that force of attraction to occur there. Now, the last type of intermolecular force that we're going to talk about tonight is a special type of dispersion force called hydrogen bonding. Now, hydrogen bonding is as simple as what it sounds like. It's when you're hydrogen and you're bonded to somebody else. But it's basically when you're bonded to nitrogen directly, or oxygen, or fluorine. If these occur, you can have hydrogen bonding, and you do have to be directly bonded to each one of these with a hydrogen. And the reasoning behind these guys is nitrogen, oxygen, and fluorine are very electronegative. It doesn't mean that there's hydrogen somewhere in the molecule and there's nobody bonded to it. It means you have to be directly bonded to it. And so what I'm going to do is take a look at this. This chart we have here, and this is a chart. It's not listed here of boiling points. And boiling points are being listed in degrees Celsius. And so we're going 0 degrees Celsius here, up to 100 degrees, down to negative 100 degrees Celsius. And then we have increasing molar mass as we go to the right. Molar mass is increasing this way. Okay, and so let's take a look at this. Water itself. Water has a boiling point, and we'll draw a water molecule over here really quickly, once again, just so you can picture it. We know it's polar. It has a boiling point of 100 degrees Celsius. Now, if we were to go to H2S, H2S is also polar, but we get a sudden drop. Looks like it's down here in the vicinity of, well, maybe like negative, I'm going to take a guess and say maybe negative like 65 degrees Celsius. Huge drop. So how do we explain the difference between water's boiling point and H2S's boiling point? Basically, it's due to hydrogen bonding. Water has hydrogen bonding, the special type of bonding, and because oxygen is so electronegative, it's causing such a polar molecule that water does have an attraction for other water molecules. And the stronger that attraction is, the harder it is to break that intermolecular force and cause it to vaporize or evaporate, or however we're looking at it. Well, now, you might be sometimes asked to explain, well, what's the difference between H2S and HES, or H2SE and H2TE? I mean, they all look the same when we draw them out, you know. Because essentially sulfur, selenium, and beryllium are all in the same group as oxygen is in. So we're really only replacing the central atom on each one of these molecules. Well, what's going on with H2S and what's H2SE and H2TE is that now you're having increasing molar mass, and now you're having increasing London dispersion forces going on, and that's what's causing the increase in boiling point from H2S to H2SE to H2TE, even though they're all polar molecules. What's going on, let's look at this other line here, is we have methane here, CH4, and then we have SiH4 and GeH4 and SNH4 here. Now all of these guys, it's kind of a similar deal, are similar in the fact that they're all tetrahedral molecules that are nonpolar. And so if they're nonpolar, the only thing that's present in an intermolecular force for these guys are LDFs, London dispersion forces. So methane is going to be the lowest because it has the lowest molar mass, whereas SiH4 is going to be greater molar mass than C2 or CH4. So, and as we go up, go from here to here, you notice that the boiling point gets higher and higher, basically because of the London dispersion forces are increasing with molar mass, and that's really what's going on there. That is our talk for 11.1 and 11.2.